Hello, welcome back. In this chapter, we're going to be looking at guidelines for putting people into groups, depending on their scores on some measure. And this is called clustering data. In order to reinforce the clustering theme, I included images of grape clusters on each slide. Just as you can visualize a cluster of a bunch of grapes, you can also visualize a cluster or a bunch of scores in a data set. Hello, welcome back. We'll look at some helpful guidelines for clustering data, and we'll learn how to create tables and graphs for clustered data. And you'll have a chance to test your developing intuitions about how frequency distributions look when they are converted to cumulative frequency distributions. I believe practice with these conversions will deepen your statistical intuitions and your mastery of visualizing distributions of data. These kinds of skills will give you a strong foundation for the more advanced topics we'll cover in this course. Hello, welcome back. From time to time in our statistical work, it becomes necessary to cluster our data because there are simply too many possible values for each score, and a table or graph of each value becomes unwieldy. When this happens, we need to follow a set of guidelines to make the presentation of data more understandable. The first guideline is to try to fit your data into approximately 10 clusters or intervals. That is, to try to break the distribution up into about 10 sets of numbers. With the small data set of people that we've been working with, it really isn't necessary to do any clustering because there are only 10 different values in the data set. But if we were dealing with scores on a GRE test, for example, the values could range from 200 to 800, and it would be overwhelming to represent every person's value on a table or a graph. In this case, we might decide to cluster people into intervals perhaps 15 units wide in order to simplify and streamline the presentation. Notice the second guideline is to create clusters containing an odd number of scores. In modern statistical work, this guideline is really just a convention. It's a throwback to a time when statisticians did their work by hand. It was easier to produce intervals containing an odd number of scores because the midpoint was a whole number, and graphing was simpler. We don't need this guideline anymore since computers do most of the detail work in creating graphs, but it's helpful for you to know that guideline because it's a convention used in your textbook and in answers to the homeworks, and it will make things clearer for you. The next guideline is to create clusters of equal size. This is sensible because your graphs will be easier to interpret. If the interval widths differ at various places along the x-axis, if some intervals were 3 points wide, and some were 5 points wide, and some were 11 points wide, the graph would be confusing. Finally, a conventional guideline is to begin the distribution with a multiple of the cluster width. In other words, the lowest score on the table or graph should be a multiple of the width of your intervals. If your interval is 5 points wide, the lowest score on the table should be 0, or 5, or 10, or some other multiple of 5. Again, such modern analyses are done with computers instead of hand calculations, and so we don't really need this guideline anymore. However, it is helpful to know the convention because it will be helpful when you do the homeworks for this unit. Hello, welcome back. We'll revisit the data set of 50 people that we've been working with all along in the chapter. And we're going to break the distribution up into 4 clusters. Each cluster is 3 units wide. So this is a good example of a bad example because, as I mentioned before, there really isn't any need to cluster these data because there are so few distinct values to begin with. However, let's create the clusters anyway so you can get an idea how to do it. In this table, you can see that all the people with scores from 0 to 2 were placed in a single interval. There are 6 people in the group. Recall, 4 people had a score of 0, 2 people had a score of 1, and no one had a score of 2. Likewise, I created a cluster of people with scores from 3 to 5, another cluster with people from 6 to 8, and so on. Recall from a prior lesson that statistical work is similar to abstract art in that we sometimes sacrifice detail in order to create a more elegant, streamlined presentation of data. I'm also trying to drive home the point that the purpose of statistics is to simplify your life, not make it more complicated. We're trying to present the key features of the data in the most elegant way possible. We may lose information with this method, and that's the price we pay for making the presentation simpler and more streamlined. But other than the fact that we created clusters of scores, this frequency table is very similar to the table we saw in the prior lecture, where all x values were represented. Hello. Here's the bar chart or histogram of the clustered data. You'll notice one thing that may seem a bit misleading is that the highest interval goes from 9 to 11. Even though no one in the group received a score of 11, you can't tell that from this graph. Similarly, in the lowest interval that goes from 0 to 2, no one actually obtained a score of 2, but you can't tell that either by looking at this graph. So some detail is lost by clustering, but the general shape of the distribution resembles the general shape of the histogram we saw in the prior lecture before we did the clustering. Hello. We produced the frequency polygon in the same set of steps we did with the unclustered data. We place a point above the label of the cluster to show how many people obtained scores in this group. For example, 6 people obtained scores from 0 to 2, so we place a point at that number, number 6, above the interval. We do the same for each of the intervals and then connect the points with a line, making sure to bring the line back down to the x-axis on both the left-hand side, the low end of the distribution, and the right-hand side, the high end of the distribution. As I mentioned before, this last step is simply a convention statisticians use to give the polygon a finished look. The purpose of this convention is to improve the aesthetics of the graph, to make it more pleasing to the eye. Hello. We convert the frequency polygon to a cumulative curve following the same steps as before, when the data were unclustered. The only difference you will note is that the categories noted along the x-axis represent groups or clusters of scores rather than just single scores as we saw before. Also, the curve is simpler and less detailed because we lost some information in the process of clustering. The simpler curve can be considered more abstract, more streamlined, and more elegant. We lose some detail, but the most important features of the dataset are visible. The cumulative percentage curve is also similar to the one we created with the unclustered data, the only difference being the categories along the x-axis represent a small range of scores rather than just a single score, as we saw in the prior lecture. Notice, of course, that the numbers on the y or vertical axis represent percentages rather than frequency counts. Hello, welcome. Now I want to give you a chance to exercise your intuition about numbers and shapes. Earlier in this presentation, and the prior presentations, we talked about scores representing the number of dates people received on Tinder. Now let's think of the numbers a different way, and let's suppose they represent the scores people obtained on a spelling test or a short math quiz. What kind of test or sample would produce a histogram that looked like this? It's not a normal distribution like we saw before, but instead we see most of the students obtain scores at the low end of the distribution and only a few people got high scores. So this is either a very difficult test or a group of people who weren't prepared and had not mastered the material that was covered. Hello. In contrast, what kind of test or sample would produce a histogram that looks like this? We see very few people scoring at the low end and lots of people scoring at the high end. So we can conclude that either this was a very easy test or we have a very able group, or both. Hello. What kind of test or group would produce a histogram that looked like this? This is the kind of distribution we see when the test items are highly correlated. People who got a correct answer for question 1, 2, and 3 also tended to get correct answers for questions 5, 6, and 7. People who get questions 4, 5, and 6 wrong also tend to get items 8, 9, and 10 wrong. So we end up with a distribution in which people either did very poorly or very well, and not many scores in the middle. Hello, welcome back. Now let's think about how different kinds of frequency distributions will translate into cumulative curves. A normally distributed set of scores is depicted as an abstract image in this slide. So what will it look like when we translate it into a cumulative or ogive distribution? Now think about that, because we're going to see on the next slide, so take a second or two. Have a picture in your head? Hello. The cumulative ogive curve looks like this. This is a simplified abstract image. Again, some of the detail is missing, but the essential characteristics are in place. Hello, welcome back. In this chapter, we're going to what kind of distribution would produce this type of ogive curve? Think about what the ogive curve represents. If we think again about the snow shovel metaphor and visualize a shovel moving from left to right or from low scores to high scores on the x-axis, collecting people as it goes along, you should be able to get an image of where most of the people scored on the test. We saw a distribution of this type earlier in the presentation. Do you have a picture in your mind of the frequency polygon for this type of ogive? Okay, if you have the picture, we'll look at the next slide and see the distribution. Hello, welcome back. Is this the visual image you had in mind? If it is, you're correct. We see very few people scoring at the low end and lots of people scoring at the high end, and we call this a negatively skewed distribution. Let's try another one. Hello, welcome back. And try to picture in your mind's eye what kind of frequency polygon would produce a cumulative or ogive curve like this one. Hello, welcome back. Is this the picture you had in mind? If yes, you are correct again. Most of the students obtained scores at the lower end of the distribution, and thus the snow shovel scooped them up very quickly. But very few people were added when the snow shovel moved to the high scores on the x-axis. So let's try one more. Hello, welcome. What kind of histogram produced an ogive curve like this one? Take a minute or two and get a picture in your mind. Hello, welcome. Is this the picture you had in mind? If yes, you're right again. This is called a uniform distribution. Each score on the x-axis was obtained by exactly the same number of people. In this case, 3 people obtained each score. It doesn't matter where you look along the x-axis, whether you look at the low end, near the middle, or at the high end. In every case, the frequency of people earning a particular score is always the same. It's 3 people. This kind of distribution is unusual for test scores and hardly ever happens in classrooms. Hello, welcome back. In this chapter, we're going to be looking at, in summary, in this unit we learned guidelines for clustering data, how to create tables for clustered data, how to create a graph or visual image for clustered data, and how to interpret curves for various types of data sets. Hello, welcome back. This is the end of Chapter 3.3 on clustered data. Next up In Chapter 3.4, we'll visit percentile scores and percentile ranks.